figure out the slope at each of those points, and that's going to be a point on my derivative. So for instance, let's just look here at x equals 2, right? This derivative is a function, so it has some value at 2. And what is that value? What is that y value? Well, it's going to be the slope of this original function. The slope of this original function is, I guess I didn't do a vertical scale, but it looks like it's about, let's just make it easy on ourselves and say that's a 2. So it goes over to up to, this is a line, it has a slope of 1. So I know that my derivative at this value is also going to have a value of 1. I'm not looking at like where the graph is, I'm looking at the shape of the graph. And notice that's true for every x value along this chunk of x's. Every one of those x values is on this line, and this line has a constant slope of 1. So the derivative is going to look like 1 all the way along that line. Now what happens right at minus 1, when x is minus 1? This function, and I messed it up with that big blob there, right, that point, but this function makes a sharp turn because these are 2 lines. That's what I intended. And we should remember that at sharp turns, the function is not differentiable. There is no derivative at a sharp point. And it doesn't have to be like a point like that, right? It can be any kind of sharp change. Okay? And sharp meaning like 2 lines, not just like a really tight curve, right? This is fine. These are not going to be differentiable. So there's no slope right there at that point. What's the slope of all of these x values? Well, this is a horizontal line, so the slope has to be 0 for every one of those. So again, open circle there, and an open circle there. So I'm just looking at each value and sort of trying to calculate what those slopes are from that value. Now here, this is a curve which has a kind of changeable slope. So rather than having these fixed slopes, I'm going to have a slope that somehow changes. I notice right here that the tangent line is going to be very steep and also negative, right? Because the tangent line is going down. So it's a little unclear, like it's not defined right at 2. Is that slope going to vertical values? I'd say maybe yes. So it's sort of asymptotic there. If you decided, well, it actually like starts somewhere down here and goes up, I couldn't argue with that either. It's not 100% clear, but it's going to be large negative values. And if I look at this point here, the slope is still negative, but certainly a larger, well, closer to 0. Sometimes it's hard talking about negatives, right? This is closer to 0, but still negative, right? And here again, even closer to 0. So to me, as I sort of link these points together, that derivative is going to look something like that. So the derivative in this case involves these 3 separate sections because we have these 2 sharp points. I'm not somehow like reflecting this curve or that curve. I'm not doing any of that. I'm just calculating what I think are estimates of the slopes of the tangent lines. And these estimates do not have to be precise for the curves. I'd say for the lines, you know, you should know that this value is 1. So your line really should be at 1 here. You know, I don't know if it's somewhere close. I'd probably still give you credit. If you gave me some value way up here, I might say, well, I don't know where you got that from. But for these curves, you know, this is the, I would say, the right graph. But if your graph looked like this, or you know, all of those would be similarly correct. Was that what you were asking, or was that just?
Yeah, that helped.
Okay.
So you're basically just taking the slope of each section, but not like, each point.
Right, each point. And then each section sort of, you can kind of blend those points together to get your curve. And then as you move to, like in this case, because we have these sharp corners, it's like 3 different sections. Some other examples, you know, the curve might be sort of smooth curves. And what we saw on Thursday was that these spots where your graph is horizontal are really useful reference points for your derivative function, right? Because those slopes are horizontal, so those are where my x-intercepts are for my derivative. So those are really like kind of dividing this graph into sections the same way these undefined points were dividing this graph into kind of 3 different sections. And with lines, you know, once you get the slope, it's the same. So the slope of a line is a constant value, right? And the constant is a horizontal line like that. The curves sometimes are a little different. So when I'm grading these, I'm looking for, have you identified these kind of key reference points correctly? And then have you gotten positive slopes and negative slopes correctly? Because that's pretty clear, right? Like for this interval, this middle section is positive. Both of these end sections are negative. So my slopes have to be something like this, right? Negative values, positive values, negative values. At that point, you're in really good shape. You've pretty much gotten the problem. I guess the only other issue would be maybe some of the magnitudes for the lines, right? Like I said, you should be able to estimate what those slopes are, but that's a very much smaller concern, I guess.
Right, thank you.
Yeah, you're very welcome. Okay, anything else? I mean, all these questions are helpful questions to me because it allows me to see a little bit of what you've been, struggling with and looking at, and it gives me a chance to do a better job of lecturing, right? Otherwise, you might as well just be watching me on a video screen, right? A pre-recorded version of me. So keep asking the questions, and I'm able to kind of use the questions to hopefully answer what you asked, but also fill in some things that I've, maybe neglected or skimmed over that need more time. So I think it's helpful for everybody with those questions. Okay. Let's spend the rest of our time here introducing chapter 3. And, in this course, we bounce back and forth from kind of conceptual ideas and questions, and then more, let's say, procedural or computational type things. And so chapter 2 is a little bit of conceptual things, like that last question. We're not really calculating anything, right? We're sort of showing we understand the concept of the derivative. In chapter 3, it's a very procedural type of chapter. What we're really trying to do here is find derivatives of other types of functions. So I think of this as derivative rules, which are really shortcuts, okay? And the problem is, right now we have this definition of the derivative, which I could write again, but we just had it, right? Here's our definition of the derivative. Sorry for the yawning. There's something about speaking into a microphone, I think, that generates that response to me. The problem is, to do that, we have to actually get kind of lucky, right? Like, we were able to do it in this case without too much trouble, but there's lots of functions where we don't really have the tools to even find those limits directly using that definition. And it's kind of a lot of work, even if we can do it. So what we'd like to do here is get better at finding derivatives, which involves shortcuts, right? Shortcuts sort of have a negative connotation, right? Like they're bad somehow. They're not bad at all. They're very useful. We don't always want to go the long way to solve these problems. And so here we're going to try and generate some shortcuts that are going to work for us and be really what we use moving forward. So after we get through a couple sections here, you won't want to go back to the definition. I'll force you to go back to the definition for like 1 or 2 problems, and I'll keep them very simple problems. But anything more complicated, we're going to want to use these shortcuts. So that's really like the first couple sections here are how do we find derivatives of functions? And so 3.1, we're really looking at polynomial functions to start with. And there's a couple properties that we're gonna notice right away with derivatives. So number 1, the derivative with respect to x of a constant. So notice I'm using my other notation here. It's just kind of an easier way of writing it all at once. The derivative of a constant. Anybody got a guess what the derivative of a constant is? So a constant function would look like this.
0.
Yes.
Yeah, 0.
Excellent answer. And there's 2 ways you can come up with this. And my guess is from your speed of responses, you are looking at the graph, right, and saying, well, that's a horizontal line, and that slope is always 0, right? It doesn't matter what the constant is, the slope is always going to be 0. And that's a great way of doing it. The second way, which I doubt anyone did because I was drawing the graph, was that you could use this definition. That's also the derivative. And both of these ways are going to be really important for us as we think about the derivative. The derivative is the slope of the tangent line, but it's also this limit. It's both of these. So sometimes our intuition is good enough to get our answer. In this case, I think that's perfectly good and fully justified. I believe it completely. But the definition would also give us that. F of x plus h is c, and f of x is c, because everything is c. And c minus c is 0. And this is not like an indeterminate form, because the top is not heading towards 0. The top is 0, right? And 0 over h is 0. And the limit of 0 is 0 as well. Okay, so we've thought about it and proved it, and so we get to use this now as like a fact. So anytime you take the derivative of a constant, it's going to automatically equal 0. How about this one? The derivative with respect to x of x. Anybody got a guess for that one? What I'm doing here is kind of starting with like the building blocks of a polynomial function, right? A polynomial function could have a constant, could have an x. We're talking about these basic pieces, and then I'm going to put them together. Anybody got a guess?
Is it 1?
It is 1, yes. And again, you could either do this by thinking about the line, right? The function y equal x is a line with a slope of 1, right? 1x plus 0. Or you could use the definition. It's only a tiny bit more work than this one. You get x plus h minus x, and the x's cancel. H over h, which is 1. Okay, so the derivative of the function x, which is called the identity function, is 1. So those are pretty straightforward. Now this one is a little sneakier. What is the derivative of a constant times a function? Now it turns out it doesn't matter what the function is. Let's see how that looks. This one we can't really use a graph because I don't know, there's all kinds of different functions and it's not clear, at least to my brain, what multiplying by a constant does to the derivative. So let's use the definition for this one. The derivative of this is going to be c times f of x plus h minus c times f of x all over h. Right? I have a constant times f of x. So when I evaluate that at x plus h and I evaluate that at x, I get this. Notice I can factor the constant out of both of these. And I have the limit of a constant times something. So a property of limits is that we can pull the constant out in front. So this is going back to our definitions of how a derivative works. This piece is exactly the derivative of f. So what this is saying is that when I have a constant times a function, I can just take the derivative of the function and multiply that by the constant. That only works with a constant, but that's a very nice and useful property for us. So you can kind of hold out the constant, take the derivative, and then multiply the function back. An example of that is, what if I say f of x equals 27x? What is f prime of x, the derivative? Now you could certainly go through your definition here, but we like shortcuts, and
27.
It is exactly 27. Now this one you could sort of think two ways. You could think, well, it's a line with a slope of 27, which is true, but you could also be using this property here, where this is the derivative of this is really 27 times the derivative of x, right? That's this property we just learned. And of course, the derivative of x is 1. Exactly. So we end up just there with 27. And we're trying, again, to build some sort of basic properties that work for kind of all sorts of functions. Okay. So we have these 3 rules so far. The derivative with respect to x of f of x plus g of x. I think I proved this in the lecture capture, or maybe I skip over it there too. You just go through the definition again, and it turns out that because you can take a limit of a sum by taking each individual limit, the algebra works out that when you take the derivative, you can also take the derivative of each piece separately and add them together. And that works for both addition and subtraction. And it comes from limits, but it's It's not guaranteed because we have to, you know, be doing this stuff, and that doesn't work for everything, but it turns out it works for sums and differences. So an example of that, let's let f of x equal 5x minus 3. These shortcuts allow me to find that derivative directly. It's 5 times the derivative of x, which is 1, minus the derivative of 3, or the derivative of negative 3. Either way, that's 0. So that gives me 5. And again, you knew that already because this is a line with a slope of 5. So there's no sparkling revelations yet, but we're close to exploring some new functions. Couldn't see otherwise. So the other thing we're missing here is, what do I do with like x squared or x cubes, right? Those are parts of polynomials, and luckily for all of us, we have a rule for that. The derivative with respect to x of x to the n, it turns out, is equal to n times x to the n minus 1. And I go through this in the lecture capture for section 3.1, and I would strongly encourage you to look at that, that proof. I may also do it in the little smaller video thing as well. So I'm not going to redo that proof of that here, but when you go through the definition and you take the limit and do some algebra, you're going to end up with this result. And it turns out it's really nice. The derivative with respect to x of x to the 5th. This rule says the derivative of x to the 5th is going to be 5 times x to the 5 minus 1, which is of course 4. And that was fast, right? Especially compared to working through this whole limit, right? You could do that, but it's actually, it turns out it's a lot of work. You're going to have to raise x plus h to the 5th, which is a really unpleasant algebra problem, and then subtract it, divide by h, take the limit, and if you do all that work, you'll get this 5 times x to the 4th. So armed with that, we can actually find the derivative of lots of kind of messy polynomials. 2x to the 7th minus x to the 4th plus 75. So my rules say I can take the derivative of each of these 3 pieces separately. That's this rule here. And we've done one here kind of like this. I'm going to multiply 2 times the derivative of x to the 7th. X to the 7th is this rule. 7 times x to the 6th. X to the 4th becomes 4x cubed. And 75 becomes 0. So we end up with 14x to the 6th minus 4x cubed. And I think in some ways it's like this was too easy. You didn't have to work very much for that. And it's a little dangerous because you kind of lose track of what this really means, right? And what this means is that this is a function that's giving me the derivative to my original function, this complicated polynomial. Every point has a slope. And if I want to know what the slope is, I just have to plug that point in here. And this is going to tell me exactly, precisely what the slope is for every tangent line to this curve. That is actually, I think if you really think about it, it's kind of mind-blowing, to be honest. Because the slopes feel to me like they're distinct, right? Like each point on this x to the 7th, I don't even have really any idea what it looks like, but you know, something like that, a little smoother, maybe not quite so many bumps, but it's potentially pretty messy. And this one tells me the slope at each of these points, every single point. So there's some kind of, I hesitate to say mystical, right? Because it is mathematical, but it feels like there's some kind of mystical connection between the function and its derivative, that they're somehow like in sync with each other because of the way that they, the information they communicate to one another. So,
would that be mathemagical?
Yes, maybe that's better. I like that better, right? Because mystical sounds kind of imaginary somehow, right? Or not grounded. But it is a real thing, right? It has a mathematical property as well as the sort of magical property. So, and again, you may not see all of that in the beginning, right? And that's fine. Don't worry if this feels not mathematical, right? If it feels something else. Calculus is often a subject that comes in sort of fits and starts, and there will be parts that sort of sync with your brain and feel like they fit, and then there'll be other parts that feel like there's some foreign object that doesn't lodge right. But over time, it all starts to come together, right? And that's kind of our job here together, right? Me to guide you and you to put in the work of sort of training and working with your brain.
Would that mean that the derivative of the area of a square would be the perimeter?
It turns out not. The derivative is a function. So if you have a function, which is like a relationship between two quantities, you know, that's when we draw a picture, you know, when we look at our GameStop share prices, right? We have a relationship there over time, right? It goes up, it comes down. And so the derivative is telling me about that relationship. It's telling me actually how fast that relationship is changing, right? So we do think of the derivative as like the rate of change. And calculus is really the study of how quantities change. It gives us an insight, this sort of instantaneous insight into how things change. And of course, things that are changing are things that are interesting to us, right? Things that are static, you know, we don't need to spend a lot of time with those because they just are what they are.
I was just thinking because the perimeter is x, or the area is x squared and the perimeter is 2x.
Yes, yes. Well, the perimeter is potentially 4x or x plus x plus x plus another x. But they are, there is definitely a connection between sort of areas and derivatives, and we will see that kind of near the end of the course. So the answer is not exactly, but yes, there is some connection there because there is a sort of underlayer, I guess, if you want to say. So yeah, good observation. One other function that I just want to mention in this section. Oh, two things I want to mention. We can also use that, it's called the power rule, for square roots and other types of non-whole number exponents. So remember, the square root is x to the 1/2. And that power rule works for fractional, actually it works for any real number exponent, but we will probably mostly just see fractional exponents like 1/2 or 2/3. It works for that as well. So the derivative here is 1/2 x to the minus 1/2. Okay, so, right, you see what I did there? I multiplied by the exponent, and then I took the exponent minus 1 as my new exponent. That's what that power rule here states. So it doesn't just have to work for whole numbers, it can work for fractions as well. And so that's important for us. An important note here is that we do not have a rule for products or quotients yet. Sums are fine. We can add or subtract, no problem, but products or quotients are a little bit of a bit more advanced for us. So if you see a product or a quotient, you've got to use some algebra to rewrite. An example of that would be like 3x minus 2 over x. We cannot take the derivative of this by looking at it as 3x minus 2 over x, because that's a quotient of two things, and I don't have a rule for how the quotient works. So sort of at the moment, I would be sort of stuck. But luckily, we have some algebra to rewrite that. I can divide both of these by x. And I can rewrite x on the bottom as x to the minus 1. And now I can treat this using my rules. I can take the derivative of 3, which is 0. And then I can take minus 2 times the derivative of x to the minus 1, which is going to be minus 1 times x to the minus 2. Minus 1 times minus 2 is 2. And then the x to the minus 2 goes down as an x squared. Now, you might have actually even noticed, if you remembered our original problem here, we had f of x was 6 over x. I could have rewritten that as 6x to the minus 1. So its derivative would be minus 6x to the minus 2, which is exactly what we got using quite a bit more work and our definition. So this is a real shortcut, and you're going to spend much of the rest of the course working with these shortcuts. So it's very worthwhile for you to spend some time with this first section, just getting comfortable and working with these rules. My last, let's see here. Okay, so the last, I think the last thing I just want to mention to get you through 3.1 is there's another type of function, the exponential function, the natural exponential function, e to the x. And this function has a very unique property, which is that if you look at it, the slope, it sounds confusing, but the slope here is equal to the function value at every point. So like at x equals 0, the function is 1 and the slope is also 1. At x equals 1, the slope is e and the function is also e. So it has this feels kind of strange, but it has this kind of unique property that the derivative is itself. It is the derivative of itself. So that's just the way it is. It makes sense sort of that there's some function out there that satisfies that. And it turns out it's e to the x. So you want to make sure it's not too hard to work with. In fact, it's very easy, right? Because it doesn't change. But you'll see that function throughout some of these questions. And you can just remember that its derivative is itself. Now, if I give you a function like x times e to the x, and I want you to find its derivative, there's no algebra that's going to allow us to combine those functions that we know of. So I can't kind of do what I did up here and rewrite it. And in fact, at the moment here, we are stuck. We don't know what that derivative is. We need to learn how products of functions work. And we will do that, but that's, well, teaser that I think is on Thursday. We'll talk about that. Okay, any last questions? Our goal is to get some building blocks here so that we are able to deal with more and more complicated functions with derivatives. And we really start to break down our limits, right? We can't find limits when we have sort of complicated functions to work with. So we need some shortcuts here that are gonna work for us. Okay. Okay. If there's nothing else, I will certainly let you go. Hope to see some of you on Thursday. And yeah, try and get those things in tonight and get off to a good start on chapter 3, which is what we just talked about. So take care, stay warm.
Thank you.
You're very welcome. Yeah, nice to have you guys here.
Thank you. See you on Thursday.
Very good.
I actually had a question. I know you helped someone with it at the beginning, but number 2 on the take-home quiz, and I just think I don't, for like the rest I feel pretty confident on, but I just feel on that one I don't think I understand it really for some reason.
But it's sort of trying to get you to